Welcome to Spring LIB.
We proceed by contradiction, so we assume that there exists a bijection, let's call it F, from the set of positive integers to its power set. So let's take an element S of the power set of Z plus, and that by definition of power set is just a subset of Z plus. We define a bit string associated to S, let's call it mu of S, which is defined as, well, the bits B1, B2, B3, and so forth, where the bits are defined as Bi is equal to 1 if I is in the set S, and 0 if I is not in the set S. So for instance, if the set were 1, 2, then the string associated to S would be 1 in the first position because 1 is in the set, 1 in the second position because 2 is in the set, and 0 everywhere else. So the label associated to S would be 1, 1, 0, 0, 0, and all zeros. Now, of course, the correspondence between the sets S and the labels that were given in this way is unique, because to every set we can construct a unique label, and from every label we can reconstruct the set by just adding to S the indices where the string is 1. So for instance, 0, 1, 0, 1, 0, 0, 0, we will need to add the second and the fourth element to S. So S will be just 2 and 4. So we can define a bijection, let's call it G, from Z plus to the set of labels, which we call L. And this map G is defined by composition of F and the labeling. So G is an enumeration of the bit strings, where the ith string is just defined as G of I. And I recall that G of I is the label that we're associating to the subset F of I. And since both F and the labeling are bijections, the map G from Z plus to L is a bijection. Now let's see what goes wrong. Let's construct a string, let's call it alpha, made of bits, so B1, B2, B3, where we define the ith bit of the string alpha to be the complement of the ith bit of the string G of I. So this is the complement of, recall that by definition of G of I, this is, well, the ith bit of G of I is 1 if I is in F of I, and 0 if I is not in F of I. That's just what we've seen in the previous page. And of course, the complement of this is just 0 if I is in F of I, and 1 if I is not in F of I. So the string alpha has the ith bit equal to 1, well, 0, 1 according to I being or not in F of I. So we've constructed this string here, but now the string alpha is a bit string, and so it must be G of n for some n, for some number n, because remember that by assumption the set of strings is in bijection with the positive integers. So alpha must be G of n for some n. Now because alpha is G of n, its ith bit is by definition of the function g 1 if I is in f of n, and 0 if I is not in f of n, where n is fixed. There's only one n that does the job. Instead, we're looking at the ith bit, where I can change. But now from this condition here, from the construction of alpha, we see that the nth bit is equal to 0 if n is in the set f of n, and 1 if n is not in the set f of n. So that's because we constructed alpha in this way. And now down here, because alpha is g of n, its nth bit is going to be given by 1 if n is in f of n and 0 if n is not in f of n. And you can see that these two lines contradict each other. And of course, the contradiction stems from having assumed that there was a projection between z plus and its power set. Therefore, the power set of z plus is uncountable.